Welcome back. In this video, what we're going to take a look at is we're going to take a look at the derivative graphs, and we're going to be describing the original graphs from the derivative graphs. So when we have a derivative graph, we can find the second derivative graph by drawing lines tangent to that graph, where we can estimate them. And then if we can also describe the original graph, increasing, decreasing, maxes, and mins. So what you're seeing here is you're seeing a graph of a derivative of a function. It touches the x-axis at 0, 0, and also goes through the x-axis at x equals 2, I think that is. Yeah, those are 0.5 is 1, okay, and so on and so forth. So when I do this first part, where I'm looking for where is f decreasing is where the derivative is negative. Well, it's negative from negative infinity all the way over there to 2. So we would say negative infinity over to 2 inclusive. It's increasing beyond 2. Local minimum values would be where it changes from being decreasing to increasing. That occurs at x equals 2. My maximum values would be positive to negative, and there's none of those. Now to describe the second derivative, to do the concave up, concave down, we've got to draw some tangent lines. So like for instance, on this first interval, from negative infinity over to 0, if I were to draw a line tangent to the graph, they would have a positive slope. And so since they have a positive slope on that interval between negative infinity and 0, we are concave up. So it's going to be negative infinity to 0. And then the other place where I'm concave up is over here beyond the 1.333. If I drew tangent lines over there, I'd also be positive. So this is union with 1.333 to infinity. I'm concave down from 0 to 1.333. And then the x-coordinate of points of inflection are where I have my change in concavity. So it's going to be x equals 0 and x equals 1.333. Derivative graphs can tell us a lot. If you can see a picture, it's really, really helpful. One more example. This one a little bit more complex. We have some changes, at -3, at -1, and then over here at 4. This one at 2, there's a change in concavity there, but it's not a change of increasing, decreasing. So it's decreasing where derivative is negative, so below -3, so negative infinity to -3, union with, and then it becomes negative again at -1 over to 4. It's positive or increasing from -3 over to -1, and then it's positive again beyond 4. My minimum points are going to occur right here at -3 and then over at positive 4. My maximum points are going to occur at -1. This one over here is a critical number at x equals 2, but it's not a max or min because I don't go from positive to negative or negative to positive. Now, concave up, it's concave up on the interval from negative infinity to -2, and then it's concave up from 0 to 2. And then it's concave up. This point right here gets a little bit tricky. It's between 3 and 4. So let's just say 3.5 for ease of it. So let's say 3.5 up to infinity. And on a test or quiz or something like that, I would specify what that point is exactly. It's concave down. On the interval, we call that -2. So let's do -2 over to 0. And then union with concave down again from 2 to 3.5. And then since we have changes in concavity at all these values at -2, at 0, at 2, and at 3.5, we're going to say all those are points of inflection. So x equals -2. It's going to be at 0, at 2, and then 3.5. Derivative graphs really not too challenging. Hopefully you understand going from first and second derivative, or going from the first derivative to the second derivative and then back to the original function. See you in class and I'll clarify.